So allow me to welcome everybody here this afternoon. And one thing about our location, our venue, we can see how nice it is to be inside this afternoon. And I want to thank everybody who's come from far and who's come from close by to give up some time this afternoon to something that we think is fairly important. And as a preliminary to the Industry Advisory Board meeting, which we have twice a year, of the Centre for Visual and Decision Informatics, we thought it'd be a good idea to get together some industry cases and your opportunity, therefore, from those industry cases to tell us more about you. You've heard, as one of our leadership folks said, the Centre Industry Advisory Board come along and listen to a lot of PowerPoints and a lot of presentations from the faculty over years, some of you. This is really turning the tables. Yes, we'll talk. Yes, we'll ask questions. But we really want to hear from you. We would like to understand better those big problems that you currently have with big data, or what you foresee coming. Now, the problem with being a futurist is that if anything you predict in a year or so may not be the case in this world in particular, but we do ask you to look at least a little bit ahead as you're thinking about this. We're not here this afternoon to solve the problems. Oh, that must have been the researchers especially. But we are here to try to hear what we think is the laundry list of big problems. How do we define big problems? Well, you could define them in many ways, and you will. But the suggested starter kit for this is really to ask, well, if it's so big, what would be really the beneficial output if it was solved? What would it do for my company? What would it do for our efforts in big data? What would it do for better understanding of our patients, for better connection between the doctors and the patients, for whatever? I mention that because we do have a case study on that particular area this afternoon that could get easily lost in the jargon of human-computer interface. But patients and doctors, we know that is an area of communication concern, has been since Hippocrates and earlier. But it's typical of the challenges that we encounter all of the time. There are many things that we would like to do. There are many things that technologies enable. There are many things I've heard in some places, such as at Microsoft, where the technology might exist, or in other companies this equally applies, but it doesn't make market sense to deliver it to that group at this time. So what are the impacts that are real for you is what we want you to put as the filter as to what a big problem is. What's a big realistic problem? What's a big hairy problem that if it was solved, it would have what impact? So a laundry list and impacts is what we're looking for you by 5:30, from you for about 5:30, and we have a mechanism for going forward on that. Saying no more, I wanted to pass quickly over to our host, who will tell you about the building that you're in. Young Moo Kim, welcome.
Thank you, Rod. My name is Young Moo Kim. I'm director of this space, which is called the Excite Center. It's a new initiative at Drexel, and it stands for Expressive and Creative Interaction Technologies. The Excite Center is just over 14 months old, so it's a very new initiative. And the vision behind the Excite Center is to bring together researchers, collaborators, students from a wide variety of perspectives. That we believe that it is through multidisciplinary collaboration that true advances can be made. So just as some quick examples, we have a piano in the corner that's actually actuated with electromagnets, bringing together the worlds of music and technology. In the back, we have some amazing digital knitting machines, which are rapid prototyping systems for fabrics and garments that are pushing the frontiers of wearable technologies. So it's a truly interdisciplinary space, and it's a privilege to welcome this group here, which I know pursues such innovative and interdisciplinary work as well. So if you would like to hear more about the Excite Center, I will be around throughout the event. We'll have other folks who can point you in the right directions to learn more about the Excite Center. I urge you to avail yourselves of any facilities that we have here. I mean, the tables, the chairs, everything moves around. If you need extra refreshments, that sort of thing, we are at your disposal. So welcome and have a great workshop.
So I'll now call upon our real host, because he carries a lot of this, and that's Dean David Fensky to open the afternoon symposium. Thanks, David.
Thanks, Rod. I don't know if you happen to have read yesterday in the New York Times yet another article on big data. It's interesting to me because the article began to qualify what big data is and what its claims are, and maybe what might be too much in the way of hype. And so one of the examples that was used by the author was something like just two completely unrelated things. It's raining in Philadelphia, and there is a data stream that says it might be raining in Lafayette, Louisiana. Therefore, something is not true, right? It just happens to be the case that both things are true. And so you can mine big data and get all kinds of correlations, and they actually don't make any common sense at all. In the final analysis, I think we have to meet our critics, and our critics are that I think are increasingly of the notion that we have to make a difference. It's not just about the analytics part of it; it's about actually what is true and how does it change the world. And that is, I think, the central challenge of CVDI and of the work we actually do together. And I know we have spent now, what, 2.5 years, Gary, it seems like about that, working on these projects, and yet we know that there's always the raising of expectations, that we need to do more, we need to do better, we need to be more novel, we need to produce ROI. But that's not a new theme here, that's just a theme of a larger society. So I look forward to our thoughts from our industry partners this afternoon about how we can do all those things and define them better and get down the road faster. Thanks so much.
Thanks, David. And I'm going to call upon the other custodian of the effort here, who we need to congratulate because we want to congratulate, that finally they've seen good sense and made our friend here Vice President of Research at University of Louisiana, Lafayette.
Thank you, and I attribute all of that to CVDI and to this phenomenal public-private partnership that we have going on here. It is so great to see a lot of new faces and a lot of old faces back here up in Philly, and thanks Rod and team here for your hospitality. As always, we appreciate it. As always, I appreciate personally the growing commitment of this community to each other and to advancing what it is that we began about 3 years ago when we came up with these ideas of doing something in the area of big data, when it was perhaps not as well defined and continues to be ill-defined. But it is our opportunity today, as it has been for the past 3 years, to put a finer pencil tip to defining what the opportunities are, the challenges are in the area of big data. And I want us to take advantage of this afternoon that we have together as we engage in this conversation, because I was at the National Science Foundation last week as a panelist on the Partnerships for Innovation, which is something that I have been on as a panel for the past 7 years consecutively. And what I walked away from that panel and from those conversations with folks from the National Science Foundation is they are looking to us for leadership in this area. They're not looking to us for followership. They're not looking to us to say execute on some of these projects. They're truly looking to us for leadership on the kinds of things that the National Science Foundation wants to fund. the kinds of directives that President and the scientific advisory community to the President will say, these are the big challenges that we as a National Science Foundation should fund. These are the tough problems that we need to move the needle on. So with that said and out of the way, I want us to have a conversation this afternoon where we move the needle, where we understand the big problems that one should solve, and why not us. We have phenomenal researchers for the past 3 years that have been working with students, and I see a lot of students, and I'm always thrilled to see students being part of the solution because they truly represent the next generation of innovators. And we want to make sure that we take advantage of this opportunity to define those big challenges and how we direct the National Science Foundation to make those investments, and how we take advantage of those investments and bring more dollars to our partnership here to address some of these issues. So with that said, thank you again. Thank you, Rob.
Thank you. Thanks, Ramesh. So we've all heard the saying that we can do anything, but we can't do everything. That's what this afternoon is about. Not to decide finally what we do, but to identify those things that we believe are important to do. And if you want a bit of sidebar entertainment, there's some ambiguity that was running around here when we're talking about what a symposium this might be. So go to your Wikipedia definitions and you'll find it's a very different definition than what we're tackling here this afternoon. The original symposia that are recorded anyway had great lashings of wine. And there was actually somebody who used to be responsible for getting people up to the third trance, that they called it. But the really good symposia went on to the 7th and 10th trance, when people stumbled home, or somewhere. Nothing wrong with that? Well, I'm sorry to disappoint you, but it's fine to have ambiguity and confusion in the early part of this, but by the end of the day, we want certainty, all right? So by the reporting of the breakout teams, we want certainty, don't we, Dean? Yeah. Okay. So having said that, I would like to introduce somebody who's kindly stepped into the fray to be moderator of the panel that we've established, our Deputy Director of the Centre, and also please join me in congratulating him again. Some of us know in the room, but also named as Distinguished Scientist this year of ACM. So Iliol Song, our leader.
Thank you. So with that pep talks, we will begin our 2014 CVDI Symposium of Big Data. Are you ready? Yes. Right. Then fasten your seatbelt. So the symposium will consist of 4 sessions. So we'll have the first 2 industry presentation and the panel discussion, and then audience discussion. And then we will have a breakout session, which will be managed by Ron. And then at the last session, we'll have a reporting of your group discussions. So the theme of the symposium here, Rod and Sian came up with interesting ideas of what key problems do we have that we cannot solve with the current technologies, but important. And then once we solve that problem, how would your view will be changing? For example, it's an extreme example, but what if your IBM Watson is in your laptop or smartphone? What can you do? What kind of a benefit? And how would your view of your daily life or your work will be changing? Or what if we can 10 billion brain neuron cell simulate in less than $100 with your laptop? So that will change a lot of our thinking and the way we work and the types of problem we can solve in different ways and what kind of benefit we will get. So we'd like to hear your opinions from industry and then academia together about those changing technology in big data problem. So eventually, at the end of today, we'll like to have what are the key problems that we need to solve, especially from your IAB or related issue, so that we can write a proposal for the year 4, year 5, year 6. And then what are the challenges in solving those problems? And then once we solve those challenges, then what kind of benefit we will get. So this is our final goal to carry with you here. So this year, this panel may be slightly different from what you have seen in other conferences. In normal conferences, panels are organized in 2 steps. So panelists present. After that, panelists interact with the audience from questions and comments. But this year, we want to change a slightly different way. We'd like to emphasize industry researchers' participation and their led discussions. So first step, we will have 3 industry speakers in each session. And then we have a distinguished panelist, and then they will begin to comment on the cases of the presented cases or their own related cases. And the step 3, we will open the session with the audience. So anybody can comment on either industry cases or panelist cases or their own cases related to those subjects. So how do we proceed? I'm the CPO today. Here CPO means Chief Panel Officer. So as the CPO, I adopted the so-called Robert Rules of Order. So in the session 3, if you want to speak, raise your hand. Then I will recognize, and then I will give you a chance to talk. But your time will be limited in 2 minutes, so that we can have a concise to the point, without having one person take over the whole floor. Right? So even later, industry panels, also when they speak, we'd like to recommend that 2 minutes per each speaker, either from panelists or audience, so that we can have more diverse interactions. So in the session 1, we have Vijay Kumar from General Electric and Lawrence James from Connexus Technologies, who is actually one of our alumni from our undergraduate program on information technology, who was also named as a 40 under 40 years old in top Philadelphia entrepreneurs. And our IAB Joe Taylor, and then our panelists Chris Dykes and Gary Edwards from Lockheed Martin, and Cam and Brian. And the session 2 will be presentation from Sue Clark, Gary, Cam, and then the same panelist. So our hope in your big data management is you dream and think big and come up with a problem and contribute to not only our CVDI but also your own IAB industries and the society too. All right. With that, we will begin with our first speaker, Vijay. Would you like to use your computer or this one? We already loaded your. You have different slides.
So we have one small change in the list of speakers. We've just been informed that Cam Ning is not able to make it. So for the panel, we'll run 3, unless Ramesh or his nominee would like to step in. Okay. You're passing? Okay. 2 other important pieces of information while we're getting set up. If you want to access Drexel's Wi-Fi, it's Drexel Guest. And if you want to access the restrooms, they're through here. But you'll need help with the men's. So ladies, lock the door. There's a code for the men's.
It's on the door right there. The code is written on the door right here. Just in case you need the second, it's 3 and 4 simultaneously, followed by 1. 3, 4, 1.
Important information. Thank you, Vijay.
I'll get started. So my name is Vijay Kumar. I'm from GE Global Research, where I work as a research scientist. I've been there for a year now. So I thought I'd spend this time introducing the audience to some big data stuff that we do at G Global Research, and then try to spend maybe the second half of my talk narrowing down on one specific use case. And I'll try to follow the template that was given, which is to identify not one single big problem, but more a set of smaller issues that kind of contribute towards one bigger problem. And take questions on that. So let's point out that Rod graciously invited us here. I'm actually filling in for my manager, Steve Gustafson, who manages a lab called the Knowledge Discovery Lab. And this is my humble attempt to give a big picture idea of what we do at G. So I'll begin with introducing, folks in the audience must have heard of the industrial internet and some of the industrial big data efforts that G has as a big bet. We provide a brief introduction and then go directly towards trying to explain what's the exact impact of the work that we do, because that's the main thing that we're interested in. Then talk about some of the deliverables that our customers, the industrial businesses, are expecting out of us. And then finally converge upon some of the big data problems that I alluded to a little while ago. So to a lot of people, G typically brings the vision of home appliances, the financial arm, G Capital. To many members in the audience, it's pretty obvious that G has industry-leading solutions across a wide portfolio of industries, including energy, wind farms, healthcare, life science equipment, gas turbines, power plants, and so on. And so over the last few years, G has morphed from being a company that has point software solutions within each of these industries towards being a more data-centric company. We realize that we're sitting on a large trove of data, and we have immense domain knowledge as to how our equipments operate and how the actual operational processes are within each of these industries. So the vision is one of creating a sort of an industrial internet, which is to try to use this rich data and domain knowledge in order to have some productivity gains and eventually some profitability gains. So how did this come about? It's mainly because of a number of trends, and this is not specifically restricted to just industry data. We are gathering more data. To draw an analogy, Netflix, for example, earlier had just information regarding what movies were rented, and that's pretty much about it. But now they have information of their streaming business as to what time of the day you're watching the movies, when exactly it's being paused, what movies are you watching at the same time, and so on. So in much the same way, we used to gather just a small set of data from our industrial equipment. For example, from the jet engines, even though these are advanced Gen X jet engines, we had only the diagnostics data at takeoff, at cruising, and landing. And this data put together was not sufficient for the aviation businesses to actually extract anything out of. So we moved from here to something that looks more like this. A lot more sensors in our aircraft engines, and pretty much the bottom line is going from maybe 2 sensors, an order of magnitude increase in sensors. That's only going to increase in time. So another trend is that we've seen the use of the power of predictive analytics, not just in regular big data, but also in industrial big data. And finally, the whole vision of how these two things come together. We draw an analogy to the consumer internet, where many things like buying a book or listening to music has been revolutionized by the consumer internet. So in much the same way, we believe an internet of industrial equipment connected to people and smart big data analytics would lead to a paradigm shift in the way different industries operate. Some of the changes expected are that operational technology could be virtualized, And the bottom line is that productivity of the employees and the assets and the operations, which is GE's big source, would be optimized in the future. So that again is the vision of the industrial internet, connecting machines, big data analytics, and the actual human loop to actually optimize the industrial processes. So coming to impact, the question of whether this is even worthwhile. These are estimates drawn by the different businesses, in that we believe in the power of one. So even a 1% improvement in the efficiency of operations within each of these industries could end up saving our customers and businesses a real considerable amount of money. For example, in the locomotive industry, just improving the efficiency of the locomotives by 1% could reduce costs by up to 27 billion over 15 years. And in a recent article by Fast Company, they cited this example where GE has a product called Teleris in conjunction with Accenture, which is more of a solution for the aviation industry, where the sensors on different components of the aircraft would relay information during landing, say about the position of the wing flaps on the airplanes and other kind of relay adjustments. And then the person who's actually looking at this information could monitor this in real time, and then relay the information back that this particular position of the wing flap is not correct. If you could move the wing flap by a certain angle, that could, during landing, eventually that could lead to several savings in the fuel. I mean, fuel consumption accounts for about 40% of the cost for aircrafts, and such minor changes are what could lead them to save a lot of money in the long run. So, towards achieving this industrial internet, the vision is to create one software platform that spans across all the industries. And as the name of the platform is Predix, and one of the premier components within this platform is how do we deal with industrial big data. And that's where the group that I belong to at GE Global Research, we focus our efforts on this particular vertical within this platform. So a quick idea of how industrial data can get big. What you see here is a gas turbine. Each blade in the gas turbine is estimated to generate easily 500 gigabytes of data in a very short period of time, talking about minutes or hours. And you have sensors mounted not just on the blades, but in different parts of the gas turbine. And you can easily see how the amount of data points generated over time could scale for a single power plant, and then we have a lot of power plants located around the world. So the role of analytics is pretty much unquestionable here. You could monitor the data coming out of a single turbine. You could zoom out and monitor the data at the granularity of the entire fleet in order to improve the operations, to make just small incremental improvements in the operations of these turbines. So before moving on, I'll just quickly set the stage as to what exactly do I mean by industrial big data. Primarily, it's meant to refer to time series data, a lot of small readouts coming out of these sensors at a very high velocity. A second kind of industrial big data could be engineering data. Folks at GE do a lot of simulations. This actually represents a simulation of how ice droplets form on the surface of the blades of a windmill. And then we have healthcare and life science data. We have a huge array of medical equipment, and we've recently acquired a lot of companies in the life sciences domain with their technologies. So I'll just mention that this kind of covers the entire gamut of things, in that here we have very high velocity data, but it's more or less well structured, and the content itself, I would say, is less per readout. Whereas at the other end, the data that's coming out of this equipment is not exactly high velocity, but then you have a lot of unstructured data out here, images, maybe videos, and the content is very high here. Even a single reading would generate very large amounts of data that you can work on. So I realize I have a couple of minutes, so I'll quickly go on to the use case. So it's a really interesting use case that I've had the opportunity to work on the last year, and this is borrowed from the life sciences, with specific implications for cancer research. It's towards finding out what's within, say, tissue samples within the body. Are there any clues hidden there that could lead to drug discovery for different kinds of cancers and neurodegenerative diseases? So at GE, we have this proprietary technology where it's called hyperplex imaging. So drug discovery efforts in clinical trials are costly endeavors. So what this technology does is to take a single tissue sample and then use that repeatedly to stain it with a whole number of chemical agents. And from each of those, you get a whole lot of images. And then the idea is to actually try to overlay images over each other and try to see what's the level of staining within individual components of these images. Each of these images are very rich in content, like tens of thousands of pixels. And they have multiple components like cells, nuclei, and so on. So the levels of expression within each of these components need to be studied at a high level of detail in order to come up with potential treatments of cancer. So I came up with an analogy, but I don't think I'll have the time to go through it. An idea of the sizes of the data. So a medium-sized study in this domain could easily produce over 3 terabytes of data, so the volume is definitely not something that can be questioned. So what are some of the challenges that we are beginning to address and what we feel are the challenges? I've listed 5 of them, and I've drawn kind of a heat map to say where we think we are towards solving them. So I must point out that we are not a group that is actually designing the core analytics techniques to address the big data. It's more of, we view the big problem as how do we make the job of the data scientist a lot easier. So the vision of our lab is to have even big data, the right data in the right form, at the right place, at the right time. So.
Right, I'm sure he has more things to talk about us. Anybody have any burning questions? I'd like to have 2 questions before we move to the next speaker. Any have burning questions before we move?
What kinds of efficiencies have you been able to extract in the last year? What kind of efficiencies, cost efficiencies, have you been able to accomplish in, let's say, the last year or 2?
So that would again vary across the different kinds of data that we have and different solutions. Some of them, for example, with the time series data, we had certain solutions in there which were actually placed into a product, and that's been so. Previously with time series data, we had what are known as historians to store and query time series data, but then they were efficient as long as data was small. But now we have more and what's known as an enterprise-wide historian capability that you can query across fleets, which is really a capability that was not even possible before. And specific to this use case, we had end-to-end analytics pipelines taking days worth of time, even for these single studies. So what that meant was biologists at GE had a very limited opportunity to actually carry out any analytics. So your study is funded for a month, and each run takes you, each analytics run takes you a few days, you're limited around 5 or 6 runs before you get the right answer. But what we've done is try to bring the analytics down to a matter of minutes or hours, made the life of the biologist easy.
Need one more question from anyone? Yes, there.
Can you talk about the need for adaptation of the analytics versus having a preset platform, you called it Predix, that applies to multiple domains, versus having an adaptive set of algorithms in each particular domain?
So I asked me to my views for this versus that. So I mean, it is my belief that with Predix, we are not putting across a single set of algorithms that needs to be. I mean, it's the understanding that across domains, when it comes down to the core analytics itself, it's pretty much the same set of algorithms used in some form, some way, form, or the other. So yeah, I mean, Predix as a platform, the vision is to support all kinds of analytics algorithms, but the research that we are pursuing is to really make it easy for the data scientist, the end user, to be able to adapt across these different algorithms for the given domain.
Thank you. We'd like to push other questions later during the panel sessions.
I suffer from device addiction, so mind me. Good afternoon, everyone. My name is Lawrence James, and I'm the president and co-founder of Connexus Technology. We help healthcare providers with tools to manage and exchange health information. Today, I want to share a topic with you that there's really no true answer for it yet, but there are a number of ideas and initiatives on the way to address this problem. The problem I want to talk about is Meaningful Use Stage 2 and getting eligible providers and hospitals to achieve what is called Meaningful Use Stage 2. The major hurdles are doctor and patient engagement of the technologies. So for those who don't know what meaningful use is, let me first read the definition. Meaningful use is a Medicare and Medicaid EHR, which is Electronic Health Record Incentive Program, to provide financial incentives for hospitals, meaningful use of certified EHR technology by eligible professionals and hospitals. In order to receive EHR incentive payments, providers have to show that they are meaningfully using their certified EHR technology by meeting certain thresholds that range from recording patient information to exchanging the records. And CMS is making $27 billion available to these eligible professionals and hospitals for achieving these milestones, which will get them to achieve meaningful use. So some of the benefits overall of meaningful use will be improved quality, safety, and efficiency, engaging patients and families around their care, improving the care coordination, and improved population health management. And that's certainly the big data play, which I'll talk about a little bit later. Ultimately, we're striving for better clinical outcomes, improved population health outcomes, increased transparency and efficiency, empowered by individuals who are taking their part and owning their part of their care. So this sounds like a very daunting task and a very daunting initiative, and it certainly is, and it's been broken down into 3 stages. The first stage, pretty much providers started getting on board in 2011 through 2013, and that involved data capture and the adoption of electronic health record systems. So that's going from, if you had a paper system or some homegrown system that was not meaningful use certified, they would be adopting these technologies and then beginning to share their records with other providers. I have listed some of the milestones, which they're called core measures. These core measures are ways how you can actually determine if your technology is meeting the needs of meaningful use. In stage 1, there were a total of 24 measures, of which 19 must be met in order for providers to reach meaningful use stage 1. And now where we are, we're in stage 2, which is 2013 through 2016, which is focused on advanced clinical processing and patient and doctor engagement. In meaningful use stage 2, we also have increased milestones in terms of participation by doctors and hitting the milestones of core measures from stage 1, but it is certainly more focused on patient engagement. Stage 3, I just put it up there because it's written by CMS, but it's most likely going to change because stage 2 has changed many times, but I just wanted to let you know that there are 3 stages at this time, and the focus is improved health outcomes. So onto onto the objective. Just going straight to it, how are we going to get patients engaged and get patients to use the tools and play their part in the care? Just so you know, one of the core measures is 50% of the patients from a hospital or eligible physician, which could be a physician practice, has to be given access to their health information and their patient records. And of that 50% who are given access, 10% actually have to do something in order for the physicians to get credit. They also have to show a prolonged, consistent use of these EHR technologies for at least 2 years. So that means the activity that these patients are exhibiting has to be consistent and has to meet these measures for at least 2 years in order for the doctors and the hospitals to receive these incentive payments. The deliverables will certainly be improved physician and patient communication, improved care coordination, and reduced hospital readmission rates. Now, doctors, they too have to increase their participation, but at least they're incentivized. The doctors have a financial incentive, and it's going to be difficult enough for them. They're already being asked to do more with less. I don't know if anyone's been to a doctor anytime recently, but if you've noticed, they're now there on their computers while they're there talking to you, trying to get this data into the system because they don't have the time to do it. But hey, at least they're incentivized in which to play their part. But what is the incentive for patients? How are we going to get patients to log into a health record system when they may not have any conditions that would require them to check their lab values or any trigger that would give them incentive to do this? Some of the things patients can do would be downloading their care summaries, updating incorrect information, viewing their patient records, or receiving alerts from their doctors based on out of range lab values. I mean, these are some of the things that could be beneficial to patients who would actually engage, but it just doesn't seem to be enough at this time. There are a few ideas currently in the industry that we're trying in order to engage patients, such as educational campaigns, setting up perks such as getting preferential treatment and scheduling, drug refills, but it just doesn't seem to be the answer as of yet. We realize that we need to make patients more accountable and have patients play a role in getting this information and owning their care and owning the data. Some of the ways that we're looking at right now are wearable devices that capture heart rate, blood pressure, and other measures that can be determined from a wearable device. And in doing so, we believe that this will be something that will encourage patients to be more of an owner of their data and more of an owner of their care. The benefits to the industry will be improved population health, better decision support for nationally high chronic conditions such as diabetes, congestive heart failure, and better access to data through the HIEs. Speaking of the HIEs, now that we have the providers up on these electronic health record systems, and we now have the technology to integrate the providers within one region, we are now moving towards having providers and networks of providers connected on a regional as well as national level. But if patients don't play their part in helping doctors to achieve meaningful use and getting the data in the system, this is going to be more challenging than it needs to be. So I come to you not with an answer, but with a question. How are we going to get patients involved so that they can play their part in this big health data situation we're in?
Okay, any questions? 2 questions? Or
Just do it. So biometric wearable kinds of devices. I'm very attracted to that idea too. But the problem actually seems to be adoption by the patients. What kinds of breakthroughs do we see there?
Well, there are a number of devices that are being tested, such as blood and heart rate monitors that can be worn, and we already see kind of as a whole as a society, people have got these Nike and fuel bands, these Nike fuel bands that we're wearing. And so it seems like it's going to require some type of cultural shift that's already happening in terms of it kind of being cool to wear this device and to be accountable for the calories we're burning, and hopefully that will lead into the culture of people being more accountable and amenable to wearing devices to manage other alerts or other things that's going on in the body, such as heart rate, blood pressure, and you have.
Do you know of any cases where the fuel band or the Fitbit have been used by physicians to monitor people's behaviors or their performance? Has there been any experiments in the medical field of that data?
So I could most certainly say that I'm sure there have been, but I personally don't know about that. I don't know about it.
all right, so we will push other questions to the later stage. Thank you, Laura.
Good afternoon, everyone. I'm Joe Chai. I'm the director of the Technology Innovation Group with IMS Health. And I'm going to apologize in advance for a rapid fire delivery because I have a lot of material I want to cover in a really short time. So what occurred to me is instead of focusing on one single business problem, I wanted to focus on what the overall challenges and opportunities are for IMS Health in the world of big data. And it occurred to me that to understand that, you need to understand a little bit about the current size and scale of IMS. So in 30 seconds or less, I'm going to explain that. I would view IMS as the anti-startup big data company. This year we're going to be celebrating our 60th anniversary, so we've been around for a while. We're a fairly big company at $2.5 billion in revenues, serving over 5,000 clients. We operate in over 100 countries. We process over 45 billion healthcare transactions per year. We source data from over 100,000 different data suppliers. We store over 10 petabytes of unique data, and I emphasize the word unique because we actually store much more than that, but a lot of it's duplicated data for different business purposes. But in unique data, it's over 10. And a fact that I just became aware of recently is that we process and store more healthcare-related data than any other entity in the world. So, when it comes to the world of big data, I'm going to focus really on the top of the quad chart because I think the bottom is somewhat self-explanatory. For the objectives, one of our objectives is merging the old and new school worlds of big data, because for a company our age, as you can imagine, we have a huge investment in legacy enterprise data warehouses. That's not going to go away overnight. It can't, realistically. So at the same time, we're merging into that new technology stacks, bringing in large commodity servers to run for Hadoop environments to complement what we've had for our legacy systems. And it's a challenge for us to figure out in the short term how to merge those two environments operationally and commercially. But we're working through that as well. And then when it comes to the term big data itself, I guess a lot of people in the industry have a challenge with that term just because it's one-dimensional. And it really connotates big, and big to me means it speaks to size or volume. And as you can see from the previous slide, big in terms of size and volume is nothing new for IMS. We've been doing that for a long time. But it's not to say that big data technology is not new to IMS. And it's the other attributes of big data technology that are what really interest us and what really challenge us. And those attributes include coping with the variety, velocity, and structure of the data. So you may say variety, well, IMS, you get over 100,000 data sources a day, you already have variety. And we do, but I would classify the vast majority of those as what I would term traditional data sources. IMS is interested in many new sources of data when it comes to social media and sensor data and video and audio data. And it's one of our challenges to figure out how to leverage that for our business. And then it's velocity. You may also say, well, IMS, you're processing over 45 billion transactions a year. That's a lot of data, and it may be a lot of data, but if you were to ask someone from Facebook if that's a lot of data, they wouldn't be very impressed. So we know that a lot of the new variants of data coming through different sources are going to bring us much greater amounts of data. And then probably the newest and biggest challenge for us is the structure, because if you look at those 100,000 sources of data, they're all structured. The vast majority are structured, and then when we receive them, we add a whole lot more structure to them. And in the big data world, we know, and particularly with social media, there's much more semi-structured and unstructured data. We deal with EMR data today. Often a lot of that is unstructured, and we know that there's more value we could get out of that than we do today. So moving over to the novelty and approaches needed. The first is on big data visualization, and it's the V in CVDI that's most attracted us to the organization, because for many years we have done a really good job using traditional visualization techniques to drive or to pull insights out of our data and convey those to our clients. And that served us well, it served our clients well, but as the data becomes more heterogeneous, more difficult to link, and much bigger in size and scale, those traditional methods start to break down, and we're in need of newer and more advanced methods to visualize the data. And then there's the flexible query capability with big data scalability. This really speaks to the human element of big data, in that IMS, as a company that's been around for a while, we're not swimming in big data scientists. We're not swimming in technologists who know cutting-edge big data scripting languages such as Hive and Python. And so we're building those skill sets, but for now we're swimming in people who know traditional BI, traditional analytics, traditional technology such as SQL. So we're looking in the interim to be able to bridge the gap by finding ways where traditional technologies like SQL query language can interface with big data technology stacks. And then finally, techniques to zero in on small targeted insights in an expanding sea of big data. Obviously, the best way to approach a big data problem is to know the business questions you want to ask, and know the problem you're trying to solve, and apply big data technology to solve that problem. And we intend to do that. But in addition to that, one difference between IMS and a startup is we have a huge amount of data at our disposal right from day one. And so we know that there's insights and important information in there that we've yet been able to leverage. And we would like to use big data technology to answer the questions no one's thought to ask yet, to find the insights in that data that we know are there but aren't accessible yet. And I'm probably out of time, so I will stop there.
Any burning questions? Yes, Mike.
You focus a lot on the technology issues in the big data, but in particular with the kinds of data you have.
Yes.
One of the issues is how do you address the fact that, say, a diagnosis of breast cancer in 2014 isn't the same as a diagnosis in even 2005. So how do you deal with the quality when you want to do the meta-analysis? Or how much effort do you put into examining those issues to actually be able to get the value out of the data that you have?
So I understand your question when you say a diagnosis today is different than a diagnosis previously. What do you mean? I don't
The
understand.
criteria for diagnosis are changing every few
Okay.
years. Guidelines change.
I understand.
Even the
Okay.
test clinical value. So say you have a clinical test, the way the test was administered has changed
Right.
over the years as well.
We definitely deal in diagnosis data. When it comes to that, I don't think our traditional businesses really look to differentiate between how something may have been classified, a disease state may have been classified in the past versus today. We use the most current data we have on our patients to represent their condition as it is today. And we have not really gotten into analysis of the nature that you suggest. That's not something we typically have done.
Although you might like to be able to.
We would, and that's one thing that newer technologies for analyzing and mining the data may be able to provide.
Any other question? I'd like to have one more question before we move. Larry.
So it raises the prospect of an intelligent agent that can mine sort of processes beyond the knowledge of your analysts and that are current, and to advise them of how the analysis may have changed or how to look at the data differently. And that's a whole separate technology itself.
No, it's absolutely something we'd be interested in because we understand that, in the small data world, which I'll term the current world, so it's not small, but relatively small. You have people who work in traditional analytics roles who spend a lot of time spinning through the data and applying various statistical techniques to understand and get out of the data what they're looking for. And we recognize that in a new big data world, there's going to be need for more machine learning type of analytics, where you take the human element out of parts of it and look at it on an exception basis because it's just too much data to look at for traditional analytics. And that's not something we do a lot of, but it's something we're interested in as we move into a big data world.
So he's telling us to apply more machine learning techniques in the CVDI. Right.
Just a quick comment. I think Larry mentioned about using intelligent agents, but I think another direction which will be quite fitting or appropriate in the context of CVDI is use of visual analytics, so that you're combining visualization with good interactive capabilities from the analyst, so that based on what they're seeing, they can kind of influence what kind of analytics is done in the background. So I think that would be another approach for what you mentioned.
Yeah, and actually the visuals, that's a short-term goal for us, Vijay. That's one of the things we're working on now for enhanced visual techniques for our data. We're sponsoring a research project with Drexel, where we're working with Xiaomei on exactly that type of research. And we've also last year had a similar and successful project with ULL.
So we'd like to see how Xiaomei's project changed your workflow or system structure later, maybe next year. Right, thank you. Right, at this time, I'd like to invite our panelists, Gary, Brian, Cam, Chris. this stage, we listened 3 company cases and a very simple, a few questions on what kind of problems they have, what kind of issues, why they have a big data, etc. So we'd like to ask our panelists, each of you can speak about 2 minutes about what you think about those 3 cases and how they are related to your own company problems in addressing key problems and what kind of challenges you are facing. So you can pick up any cases from there. Who would like to begin with? Ryan? Okay.
I'll go first.
Yeah.
I'm going to point some of these questions towards specific people, but I think they're more general questions that everyone looking at big data may be interested in. I guess the first one would be really probably for Lawrence and possibly a little bit for Joe. So Lawrence, you were talking about patient engagement, you were talking about things like sensors for patients and understanding what the community really does. I guess the question that I'm interested in is, as we begin to collect a lot of big data through these methods, we can't use what I would call traditional scientific method hypothesis testing because the sample sets don't necessarily lend themselves to repeatable testing. And I'm kind of curious what you think the real challenges with big data analysis are associated with that.
What are you saying? The chat.
Red. Thank you.
Thanks. Just if you could summarize the last part of your question, the challenges with.
Well, we're getting a lot of data, and that data isn't necessarily well designed or well sampled. So, how does that impact the type of analysis that we can do, using these kind of ad hoc sensors that will collect a lot of data? I mean, another use case would be, associated with kind of medical treatments.
Right. So it sounds like you're saying we're getting in a lot of data from a lot of different disparate sources, and how can we derive intelligence from that data from these disparate sources when, the way it's coming in or the format will not always be consistent. So the way we address that at Connexus is through pretty smart ETL tools, which basically allow for flexibility in the data sets, in terms of the formats of the data sets that are being fed into our data repositories. I think that, we are going to have to need more intelligent ETL tools that are going to be more flexible in regards to the types of data and the formats of data that can be consumed in order to perform these analytics. And I think that we're going to have to focus a lot more on data normalization, as we're bringing the data in from these different disparate sources, if we're going to be able to do anything intelligent with it.
I guess my question was actually a little more about selection. So, in your typical scientific experiment, there's a selection criteria, and then you test, and it should be repeatable. I think in some of these real-world cases where we're just collecting data, from sensors, without selecting kind of the community first, how do we develop knowledge as a society from those cases?
Isn't this the real difference between discovery and hypothesis testing? So, in the case of sensors, you may be collecting data having no idea what your hypothesis is going to be.
I think it is, but I think it's at a scale that we haven't seen before. And I'm just curious what others in the audience think, because we're able to do this now, whether it's collecting patient information, or whether it's collecting information from engines on aircraft that may or may not fly.
Gary, would you like to comment?
Well, I'm not sure if this is okay.
I think you are.
So I think one of the issues of data diversity
is that we'd like to be able to provide the same kind of democratization of analytics that we have in democratization of data right now. You know, we're providing data in a lot of big masses of data, but there's not. I understand the notion of smart ETL tools, but the reality is that we're still in the zone where it takes a data scientist to really put together the conditioning of data, the normalization of data, in order to really bring the algorithmic approaches to bear and to produce an analysis. VJ talked, for instance, about the cost of trying to do 5 or 6 runs. That by the time you spend days or weeks doing a run, and you try to re-ingest the data, renormalize the data, do new kinds of feature extraction, try to find out the best sets of features that are likely to support the algorithmic analysis you're trying to do, choose alternative algorithms. 5 or 6 runs is not a lot, right? And so we're really limited by those restrictions to the kinds of problems that a data scientist can do. And we're far from being able to do the kinds of applications where an analyst or a user can really put his own hands on the data and put together the analysis he needs to do. And I think that one of the things I'm hoping comes from the work that we're doing is that that business processes will be able to answer questions by assembling the right collection of data and analytics in a particular case. And I think we're still fairly far from that.
I think one of the difficult issues in managing big data is how you define the workflow in incorporating existing conventional structured data and then new unstructured data together to define the business value. Yes, Bob. Yeah.
Hi, sorry about that. Bob Boland, Johnson & Johnson. So, Gary, that was a good point. One of the things we're looking at now is sensor data, right? And the direct-to-consumer products like Fitbit, you have these patches that people wear. They're good for the everyday user, but we're more interested in getting into the raw data. So we've been in touch with companies like Philips to get into their APIs. They're very sensitive to these APIs, but we're working out deals where we can get to that raw data. And exactly where Gary's point was trying to go was, getting to that raw data is the key, and to really unlock these algorithms that we're trying to work on. Thanks.
All right, next, Cam, would you like to?
I want to shift the gear. One of the challenges and problem of big data set is the quality of data. A lot of time, particular sensor data, you don't have the opportunity to acquire those data. That's number one. Or number two is, even though you know where the data is, because of proprietary, you could not get over data. So these were two problems: quality of data and the uncertainty or missing data. How do you fill the gap? So far, the team has been working pretty good on the analytic of the big data set, but have not addressed to the problem. How do you fill the missing data? How do you account for the uncertainty of data? And how do you validate the quality of the data? So those are 3 common themes I expect each of us will face with.
So within the government space, I think our challenges might even be a little bit more high level than some of the challenges that y'all face. VJ's presentation was very good, and it sounds like GE's doing some amazing things. The challenges that they seem to have are very much at the low level. How do we get these data sets to do exactly what we want them to do? From my perspective, the things that I face are a little bit more in line with, we kind of had a KPMG study that was done recently that we all kind of read over before coming here. And it talks a lot about legacy systems and inability. The largest share of respondents, this is from the study, consider integrating data technology into existing systems and/or business models to be the biggest challenge their companies have faced regarding data capture. That, to me, within the government space is very difficult. 400 systems that were created over the course of 25 years, And there's a lot of really cool, sexy stuff happening in big data, but the reality is what we have from the past. And how do we bridge that gap? Those are the real challenges that we face. The governance that it takes to get from where we are today, and the procedures and processes to get to where we can start doing some of this new stuff. I tend to liken it to kind of living in a hoarder's house, and all of the craziness and chaos that comes with that. But then stepping outside of our house every morning in a suit and getting in our BMW and going and talking about the things that are really cool and the things that can happen. But with all these huge challenges back at home that that we try to hide. And I think that aside from some of these companies that are really on the forefront, I think that represents a lot of the realistic challenges around data and analytics and how we get from point A to point B. So to me, and I'd love to hear from others about similar challenges that they face. And then given that I'm CIO for Department of Health and Hospitals, I have to comment on the meaningful use presentation. It's good, and I tend to struggle with that whole aspect of the industry and whether or not government money being flooded into that market is good, but sometimes I feel like it maybe took the eyes off of the ball and pushes everybody a little bit towards these very specific goals that meaningful use brought to light, as opposed to some of the things that we could do to really change the game, especially around getting ownership of the data to the individuals so that they actually feel like they own their own health. And touched on a lot of things in your presentation. How do we get biometrics to be popular? And I just feel like we're kind of there's some really exciting stuff there, but I feel like we're on the tipping point and not quite there yet. But there will be some good technologies that kind of get us over the hump to where everybody really wants to know about the quality of data that's out there.
Right. Thank you.
So I'd just like to comment maybe from a slightly different point of view on Chris's comment. So I saw a nice factoid the other day about the use of the term big data. And a lot of overuse of it. So this particular factoid was around, someone had counted up the number of times it was used in investor communications. And I guess between 2012 and 2013, it increased in usage by 44%. So once all the investors for public companies are talking about this, we know that there's probably a little bit of work to define what that actually is. Look back at cloud or Web 2.0. So I think your point is well taken. I think there's a lot of sort of hand waving around this, and maybe we need to deal with some of the existing challenges. But I would say that the other point of view there is I think there are some really interesting technologies. I also enjoyed Vijay's discussion, and I think one of the challenges for this group is to understand what are the technologies and what are the significant aspects of big data that aren't just buzzwords that we need to really be looking at. So for instance, Vijay talked about real-time data versus looking at later analysis. He talked about size and complexity versus velocity of data. And I think that really ties back to some of these questions around, what do we have available today in terms of compute power, bandwidth for collecting data, and I just asked the whole group to think about what are the most important aspects or elements of big data, within those types of contexts, because I think that will actually help us define what we ought to be doing to sort of get from, where Chris is describing to where we ought to be.
All right, at this time, we'd like to open the panel to public. Any audience, David?
So in a sense, to Brian's last comment and to Gary's earlier one, it seems to me that the answer is not compute power by itself. Rather, I think scalability is more often about understanding the patterns of queries so that you can you can optimize repetitions and then push the data scientist role down into the analyst role. So I think Gary was really talking about the scalability of knowing the answers to enough similar questions that you have the tools and the scalability to repeat them many, many, many times. Whereas I think raw compute power is likely to be inefficient in the end.
I think, my bias, of course, is in healthcare, but I think healthcare spans across a number of the issues you raised. The Department of Defense and Health and Human Services, one who runs TRICARE and the other who runs the VA, just gave up after about $1 billion on trying to integrate their healthcare systems. Now that's a lot of money around the technology and without coming up with a solution. The issue that we are talking about is a lot of technology focus, but the problem, which gets to one of the points that was raised, is linking EHRs, whether they're all current or they're legacy systems, isn't necessarily going to solve healthcare problems because the EHRs aren't necessarily collecting the right data. And we haven't invested anything, really, in figuring out what's the missing data to solve the healthcare problem. And so a lot of the big data focuses on what data is available, and we can overwhelm the technology with the data that's available. But part of the goal, I think, is to understand what's the problem that needs to be addressed and what are the steps that can lead to bringing big data in. But how do we make sure that that's on the right path and not just something that becomes a technology diversion that we focus on?
Any other comments from the floor? Yes.
One thing, to take a point that Chris sort of dipped his toes in the water that you followed up on, and that is that I have a concern that sometimes the money and the time and the effort is gyrating toward the sexy stuff, as Chris brought up, as Chris called it. And it worries me sometimes. I mean, for example, last month, we could have saved 294 lives if we simply had a way to find a black box in the water. It doesn't get any less sexy than that, but it sure would have helped. So I worry a lot about the gravitating toward the sexy stuff, toward the really dynamic stuff, and that we lose focus sometimes on the stuff that can really be of benefit and might be simple to get.
So how we get the cost-effective solution for big data? So finding a deal. I think someone mentioned that only 0.5% of the data are analyzed, but a lot of data are spurious. So your big data pre-processing module need to find out what data to extract and then integrate with the existing EDW data or business data. So you need to define good workflow to extract the data.
I would add to that Vijay cited the acquired domain knowledge that their organization has from their working in analytics across a number of domains. And that domain expertise comes to play everywhere in the process. The ETL functions, what features do you intuit are likely to have prognostic power? You're making decisions early, and there's not, without that human insight into the problem, we're not going to get beyond fairly static business process impacts.
I think what Ken mentioned, there are missing data, and Michael says that EHR system is not collecting right data, etc. So how we solve that problem? So in academia, one of the techniques we have adopted in solving those data, finding right data problem is using ontology. This is why we developed a lot of medical ontologies, healthcare ontologies. So we extract the data that are related to ontology. So we think that is more relevant. And then we feed into our data model, process model to process it. Yeah, Vijay.
I just want to also direct what we are talking about to a broader issue in terms of value. There's been a lot of mention about using big data to make things more efficient, to reduce cost, things like that. But if you look at it, in terms of innovation, I think that from a marketing or business point of view, you can do better by cutting costs. You can get value by improving your existing products and satisfying your existing users better. And that's another type of innovation. And then even beyond that, you could try to say, how can I use big data to really open up new markets that don't currently exist? And sometimes people refer to this as kind of a disruptive innovation. And so I think that we are looking at data mainly in terms of what you currently have and in terms of reducing costs, but I think we should also look at value in other ways.
So examples of business value is like reducing cost, finding new revenue, finding new business model, increasing speed of service, increasing effectiveness of interfaces and service, and customer satisfaction. So there are many types of business values. So I'm not sure whether industry has any taxonomy about those business values when they apply big data projects. Any other questions, comments to our presenters or panelists? Okay, one last number 10.
So far, none of us talk about what is the purpose of big data. I think in the original of the big data, right, there are three purposes. One is to understand those data sets. How do you extract information, make it meaningful to construct some physical understanding? That's number one. Number two is to visualize. Given the big data, how do you see it more useful so that you could give you the information? Third is forecasting and prediction. Based on that data set, how do you use it for further using that information to do prediction, modeling? Okay, so those are the big three things: understanding, visualization, and forecasting, modeling. So I think that's the framework that we are working on. That was 2 years ago when I was with DoD, with NSF and all those. That was the purpose of that. And I understand as of today has not changed. That three goals have not been changed. So that are our focus.
Thank you, Cam.
I know you said that would be last, but I just can't resist. Cam, I like the framework you just proposed very much. I will quibble with one element, and that's visualization. For me, informatics, we talk about informatics rather than big data for a minute. Informatics is about content, it's about computation, and it's about cognition. And I think you're touching on this hints of that, but I think we have to go farther. We have to talk not just about how new metaphors for visualizing information, but how do we change how people interact with massive amounts of information far too large for them to manipulate themselves. How do we create, in the military, there's something called the OODA. It's observe, orient, decide, and act. And, the orient, the observe, we collect all the data. But it turns out the orient piece of the process is the difficult part. How do you gain a grasp of the operating problem that you're dealing with in order to understand its nature and understand where you need to drill in to work the problems? And how do we orient users to massive amounts of big data? It's probably not just through visualization. It's probably through more interactive processes. How do we bootstrap discovery of new models? Again, going back to domain models or to domain expertise, we're probably going to have some way to inject some human manipulation of the information to start to bootstrap that process of discovering new models. So I think that's a subtle but important distinction. But I like the framework very much.
It's not my credit, it's the POD credit.
So that's exactly what CVDI is trying to do, right? So understand, predict, and visualize. That's what CVDI projects are trying to achieve. All right, with that, we will complete session 1 of the panel. We'll take a quick 5-minute bio break, and then we will come back for a short second session. Thank you. Please give a big hand to our panelists. All right, so hope you had some good break. I see many people are still drinking, eating. So I think we can do in parallel processing. In big data, parallel processing is a must. So in our second session, we have our first speaker, Sue Clark from SunGard. She will give her cases for 5 minutes. So each speaker will have 5 minutes again. And then also we will have a panel session. And then we'll open the discussion to the floor.
Good afternoon, everyone. What I'd like to talk to all of you about is one use case that we've been working on at SunGard and have had a great deal of success with regard to the marrying of importing large amounts of data from external to our needs and marrying it with our internal customer information so that we can provide benefit to one very important aspect of our business. For those of you who may not know, SunGard Availability Services is responsible for making sure that customers always have availability to their data. So in the event of any kind of a disaster, be it a natural disaster or a man-made disaster, a lot of our customers come to our data centers and do their work within our data centers by bringing their tapes. We have all the equipment, we've got the office space, we've got the telephones, so it's just as if they are working out of their current offices, even though they may not be able to at the time. For instance, in Hurricane Sandy, as a much more recent example, customers were flooded out of their data centers, came to our data centers up in Carlstadt, New Jersey, and were able to be live with their data at that point in time. So one of the things that the crisis management team who manages that interaction with the customer brings them into the appropriate data center for doing their recovery, came to us and said, is there any way you can help us out and tell us, in the event of any kind of a natural weather condition, who our customers are that are affected by it? So we went and looked at the NOAA data, and we started out looking at tornadoes, then we brought in earthquakes, hurricane information, and then they liked that so much they wanted even more. So what we were able to do this was the result of our efforts over time, and we've displayed here 6 months worth of data showing where the various natural occurrences are: tornadoes, hurricanes, wildfires, and then other weather alerts. What we then did is we took our customer data and mapped our customer data to each individual condition. And we provided that information with the location of the customer within a 25-mile radius of any given weather pattern, and then what data center they were due to recover in. Then we took that information, married it to the customer's contract information so that our data center people can just click on that and see what equipment they need to have ready for that customer in the event that they declare a disaster and come into our data centers to recover. very specifically, what they're able to do is drill in on the specific weather event. They can click on this, there's a link provided, it takes them to the NOAA site for all the key details about it. Then each of these blue dots represents one of our recovery services customers within a 25-mile radius of that event. And this is an example of a wildfire in California. As you may or may not be aware, there were a number of these last summer into the fall, and we had to be aware of these and where our customers were relative to them in the event that they needed to recover in one of our data centers. So overall, what we were able to do is bring in large volumes of data. We took every single zip code in the United States, there are over 40,000 of them. We mapped the distance from each zip code to each other zip code, 1.6 billion rows of data. Each zip code has longitude and latitude associated with it. We were then able to take that information, and every one of our customers has a zip code and map that longitude and latitude. Then we were able to use mapping techniques to be able to determine the radius of that customer from any given weather event. So we were able to not only do this for our internal use, but then last year we developed a way to push it out externally to our customers. We now send a customer an email if they are one of the blue dots in near any kind of a weather event. We tell them in the email subject area what the weather event is. In the body of the email, we tell them what of their data centers could potentially be impacted, and we give them a link into their recovery services portal where they can then go see all the details associated with the weather event and determine whether or not they want to put themselves on alert or whether they need to declare a disaster. So we've been able to take something that we developed internally for our use and push it out for external use for each of our customers. They've been very happy with that.
Thank you, sir. Right, any burning questions? Yes, Rod.
Wow, this is a great project. So for the past 4 years, actually the past 2 years, we've been working on a project with the NIMSAT Institute at our university. We're building a national scale information sharing platform between the public sector and the private sector. Today, the public sector has a good incident management structure and system and process in place. And the private sector has good processes in place to monitor the weather event. For example, if you take a store like Walgreens, the fire alarm goes off, the competition would know it. But unfortunately, there's a big gap, information exchange gap between both of these. So we actually have an effort going on. We actually did develop something called Louisiana Business Emergency Operations Center for our state. It's an information exchange platform that was built in our state under the leadership of Dr. Koluru. And now we're taking it to a national level. And what would be really interesting is what we're also trying to do is bring some of this big data research into understanding better situational awareness from social media. For example, yes, you will know some of these weather events from NOAA and other sources, but in order to understand through social media, using like Ryan's project, for example, understanding, what events are actually occurring there, on the ground, whether it's power outages, whether it is, there are no hotels, the gas stations are out of fuel. I think pulling that information also into this, through some of our CVDI projects and adding to this would I think be of great value as I see it. So.
Yes, absolutely, and it's RSS feeds for news events, bridge closings, anything of that nature that it impacts the ability for people to do their day-to-day jobs. Yes, absolutely.
So two comments. One of them I have to be vague about because I have an NDA with that company. That's one of your competitors. But the idea there is to actually work with utility companies to predict where they should pre-position their crews before an electrical event happens. Because after the event has happened, they have the same problems getting to fix the problems that the normal public has, right? So that leads me to the second comment, is that we might want to look more deeply at some energy companies, and there are several local here, big regional ones here. There's a big regional grid right north of here, and some concentrations at the Navy Yard around the energy and energy grid and energy institute kinds of ideas. And we might borrow some of the climatology prediction capabilities involved with energy for use with data.
Absolutely, yes.
Right, thank you. We will defer other questions to Sue later. Here.
So I actually brought two example areas, I'll call them, rather than case studies. You know, my group is really focused on research at how, into how big data techniques can be used in national security areas such as intelligence analysis, as well as in some of the business processes related to Lockheed Martin's business lines, product lines. And there are some interesting similarities between them that I want to draw out. So I'll just quickly give you a kind of hand-waving description of a couple of the kinds of problems that we work on. So one is surfacing the behavior of groups. Imagine, I'll give you a somewhat realistic example. Imagine that you're in a mountainous country that ends in a stand, and it can be any of them, I guess, at some time. And there's a lot of data being collected. A lot of data about known bad guys, or a security stabilization kind of area, trying to primarily fight corruption that's undermining stabilization, right, and criminal activity. And analysts are getting exposed to a lot of data. Who are known bad guys? What's their social network? What's their kinship network? What's their tribal network? What's their communication network? What kind of communication devices are associated with vehicles? What people are associated with those vehicles? What do trace route data on communications, on their internet communications look like? Huge multidimensional networks. How do you find the interesting patterns in there that might let you answer a particular analytic question? And the state of the art of the things that we were doing a few years ago were to get all that data from the field, get questions from analysts that might be something like, is there a network built around this couple of people, maybe? And so there's some hypothesis, and then how do you then condition the data so that you can apply things like maximal strength clique analysis algorithms to try to find the sub-network that you might then hand back to that analyst and say, here's a view of the problem space you might look at. So that's the kind of stuff that we've been doing, but what we really want to be doing is we want to be able to take a much more data mining oriented view at bootstrapping this process of identifying behaviors and activities that are hidden in the noise of everyday massive transactional data, say. So looking at insider trading, for instance, looking at money laundering, those are other examples. Looking at an information campaign in social media, something we're actually working on right now. How can you tell whether an information cascade is something organically going viral, or is it an orchestrated information campaign? And what these have in common is they're all about finding structure that's hiding in the data, and that structure can be used to either, today to try to confirm a hypothesis of something causal, or what we'd really like to be doing is from the correlative evidence being able to synthesize hypotheses about the causality. And another, what seems to be quite a different domain,
and one that VJ will appreciate, I know. It's something we are working with GE in fact, and that is looking at analytics in the product sustainment. As you know, Lockheed Martin sells aircraft, and so they also build ships, they build missile systems, defensive systems of all types. How do you sustain these things in a more cost-effective way? It's been said that the size of America's aircraft fleet will be determined not by the cost of the aircraft, but by the cost of sustaining those aircraft. So if we can't make those processes more affordable, ultimately it affects our mission readiness around the world. So what we're looking at is using big data to try to enable entire new business models. So rather than, I mean, you know how your cars used to be, right? You'd have scheduled maintenance every 3,000, 5,000, depending on how rigorous you were with your maintenance schedule. But now you're starting to see these kind of health minder functions in your cars, right? That say, well, your oil percentage is at 60%. You don't really need an oil change right now. And so that kind of more data-driven process for understanding how you could reschedule the business processes, and with them, the spares, the inventories, the manufacturing acquisition buys, the training processes, all the elements of the business processes that are impacted by those, by that ability to perhaps defer or optimize the sustainment processes. But to do that, key piece here is, how do you find the evidence in the big data? So it's one thing if you're interested in saying, well, you know, I could optimize by modeling better expectations. If I can understand that, you know, 2005 Honda Accords are more likely to need this kind of maintenance after a certain amount of time, that's certainly a reasonable thing to do. What I'd really like to know is that my Honda Accord is going to need a new ball joint in 25,000 miles. Because if I could predict that and it wouldn't break down on the road, a weak example, I know, but if I could tell that that pitot tube overheat on the C-130J is actually an indicator of another controller failure that's much more serious, and I could schedule the maintenance around that at a time that optimizes the other business processes, that's a valuable prognostic to know. But how do I discover that prognostic? So it's that same problem. How do I bootstrap this thing? You know, the two ways to do it right now are either the brute force way, which says I generate a whole bunch of features from the data, and I try to run as many of those features as I can against as many different kinds of modeling mechanisms as I can, and I get back to VJ's 5 or 6 runs as about all you can do problem. If I have domain knowledge and I can trigger a specific hypothesis about where there's a causal relationship and then use the data to try to confirm that as a prognostic, maybe I can do better. But what I really like are ways to kind of, from the data, being able to find the correlative evidence that, again, would help me synthesize the hypotheses. So I know I've gone over my 5 minutes, so I told you.
Any burning questions? So everybody understood his problems?
Yeah.
You want?
Yeah, I just have questions that Gary's mentioned about like data and statistics from the features of data. I just wanted, because in terms of data mining or as learning, we have to turn the data into different kind of features. I just wonder, could you clarify, for example, what's the difference, as you mentioned, data versus features about
So in the logistics case, for instance, the data, the raw data might be specific system signal measurements, and then there are just a number of statistical aggregations, trends, sliding window analytics that we apply to generate different kind of statistical features on those. In the intelligence space, it's much more difficult because there tend to be very specific discriminators that are specified. I probably can't say more than that. I mean, not because it's ultra sensitive or anything. There's not a crisp way to talk about it. But you know, you can generate a lot of statistical features from data, and especially if you're talking about combinations of data. They're not all meaningful. They're all expensive to generate.
So how do you find
How do you find disruption in big data? So a lot of the examples we talk about are really about cost efficiencies and deriving value from existing data. In some ways, you're looking for it to start with. There's some reason you're looking for it or some domain you're looking in.
Right.
How do you discover a disruption, it being a form of innovation that it just happens? So, you know, it's a bit like saying, how do you plan serendipity?
Well, so two answers for the two domain problems here. If they don't fly out of my head. In the intelligence area, it really is, there's a big emphasis, and I think I have this on the slide even, in looking at normalcy models, of building up what in the intelligence community you call patterns of life, right? And then looking for deviations from those that are meaningful. Particularly if you can get those different indicators of those that that highlight different facets of the same underlying causality. So, you know, we had an example where we were looking at a combination of social media sentiment and topic theme growth at the same time that we were looking at shipping traffic of all things. And well, and so in that case, there was a correlation between an unusual change in sentiment in topic density in social media communication with unusual traffic patterns in shipping traffic. So that's one kind of thing. In the logistics data, and there's a difficulty with this, but it's looking at data for failures, right? I mean, being able to use machine learning to back compute the model from observed failures and the difference between pre-failure, failure, and post-failure behavior of the same systems. And the difficulty of that is we don't let things fail a lot, right? So it's hard to get, even though you may have massive amounts of aircraft data, you know, more than 99% of it is good system data. It's hard to find learning examples in the data.
But all patients die.
Aircraft just reached the end of their serviceable lives.
They're going to get redundant.
Right, let's give a hand.
Thank you. As most of you know, Light, Louisiana Immersive Technology Enterprise, we do a lot of virtual visualization. One of the new areas that I want to bring in, the new project is called the monitoring. It's very close to what Gary talking about, condition-based maintenance, right? In the DoD, they have done quite a bit of that. What we are going to do is bring that sensing and monitoring to the oil and gas industry. So the objective is to develop the method to detect and classify time series data from the sensor. Whatever sensor you put on the oil rig, could be temperature, flow, vibration, acoustics, whatever data. They are in the time domain, right? So one of the things that challenging for us is to detect the condition is normal or abnormal based on those sensing information. So the goal is to apply those data set, detect those, and particularly we are using it to look at rotating machinery, such as pump, compressor, as well as more stationary mechanical component like pipes, tank. The problem with the tank and pipes is corrosion. We could not afford to have those mechanical components corroded in the seawater, in the open environment. They will be corroded, so we want to monitor the health of them. So the approach of things we needed is extract fault features. Okay, so far this group has done quite a lot of analytics, but it hasn't got into the area of how to extract abnormal features from the data, from either time history or frequency domain data. How to extract those information. Now the extraction is not straightforward because you want to see the thing starting to deteriorate. when the thing fails, it's too late. You already know. I mean, if the rig or oil gas explode, you know it's already happened. You want to see it gradually going bad. So that is not an easy problem, right? So detect and classify technique, in particular looking at the information, starting gradual changes, how to isolate the information, background noise, contamination, fault data, false alarm. How do you differentiate? Those are the data you're looking at. What are the data you are not? The contamination. So extracting those features, see what is abnormal, what is not normal. What we are looking for is the method and also robust signal processing. Signal processing, a lot of people have been using that for different applications. In my former job, we did undersea, a lot of underwater signal, acoustic event, right? A lot of signal processing. Again, how do you extract the information, either the time domain or frequency domain, or another transform domain? Okay. There are cases that you want to transform the data from not the time, not the frequency, but into another domain so you could extract those features. Benefit of the industry, of course, that will be helping them to monitor the health of the oil and gas, provide safe, affordable, again, the cost. Very similar to the condition-based maintenance. Instead of you doing a scheduled maintenance, you do a condition. When anything going bad, you pull it down, you stop the operation. It saves you in the overhaul and also the shutdown condition. So saving, safety, cost, and reliable. Because you do want the plant to be operated 24/7, 365. So any of those extra information you could extract will be useful then. Okay, this gives you the picture of what we have in mind. Let's say you have an oil gas rig in there. We want to monitor putting sensor on the machinery, either machinery, rotating machinery, or stationary tanks, pipes, and so forth, sensors, all kinds of sensors, pressure, temperature, fault, acoustic, vibration, and all those, corrosion sensor too. And then from there, we want to detect from the signal, detect is there an abnormal problem. And then once you detect, classify, what's the problem? Is it corrosion, or is it one of the mechanical components, the gear crack, or things starting to deteriorating, worn out, the gear is missing, whatever. But on the other side, we also have a model, a predictive model, based on information to form that model. And that model to tell what is normal and what is not normal. And we fuse the model and data. On one hand, you get the model, on the other hand, you get the data. The data stream and the model, they correlate. They kind of compare, looking at that, you do correlation between the model and also the sensor data. So the model data fusion part is give you the information that you want. Provide a warning if there's a problem, detect what's the problem, classify what's the problem, and then the next, the most difficult one is live prediction. If you detect there's a problem, how long we could leave that alone without doing any interference? That's the most critical part in the condition-based maintenance. How do you forecast that kind of remaining life? Let's say if this could survive for another 6 months, do you need to shut down? No. If they say, oh, in any minute, you better shut it down. So that is very important for the operator, how to take the corrective action. Another thing we would use this model is for human body, human physical health. We input sensor, whatever remote sensor or smart sensor on the human body. One of the projects we started to work in is with the voice center at Baton Rouge. Is the vocal cord that has certain muscle to give the sound production. If the muscle is weak or abnormal, it will be a rise of abnormal speech problem. So we work with the doctor. On one hand, we want to scan the vocal cord, and we have a model to build what's a normal vocal cord should be. The comparison of those data and the model will give us a handle of how to diagnostic that kind of problem. To diagnostic the problem, and if so, what's the problem? And we also carry another step. Given there's an abnormal condition, how do you modify the muscle or whatever, or the organic structure in order to make it normal? Okay, I'm almost there. So instead of doctor trying to error, the model and sensing give you a better handle of a paper or experimental work on how to fix the problem. The last slide. The other problem applies the geo problem for oil gas well to identify where they are. We get tons of information from either pressure, temperature, or the concentration in the ground. So using those information, how do you come up with the correlation that is the source of the oil? Where's the source is gas? Or that is a fault in information. Just like the false alarm, right? So summarizing the problem is dealing with how do you extract the information from quality data. There are times you might not have the quality data. There are times you don't have the data, complete set of data, missing data. How do you do the uncertainty of those information to fill in those missing information? How do you build that data in order to extract those information? And using those data to predict or forecast. Okay, I'm running over.
Thank you. Any burning questions?
So Kim, there's been a lot of work in previous on the classic false alarm problem, where you set some kind of threshold to some indication of some condition, and then you process the alarm to see if it is false or correct. And certainly a lot of work in signal processing history. What's new here, I guess, is massive amounts of data and perhaps lots of dimensions of false alarms to be looked at. I don't know if there's a question here, but it seems like a classic false alarm.
Well, I think that what you are trying to ask is how do we minimize the false alarm? Okay. Now, the false alarm is you base information to make that decision classification. The misinformation could be due to several reasons. One is you don't have a good quality data set. Okay, the data is contaminated with a lot of interference, background noise, or interference from the true signal. That's one source. Two, uncertainty. What you measure, you thought you measured that, but actually you might not measure that. So the information feed into that is not what you're looking for. So you're looking at not the data you wanted to look at. Okay? This is different from the first set. The first set is a quality problem, missing data, quality problem. The second one is you're looking at the wrong data, wrong information. Your lens is focused on the wrong thing. Okay? So that's also causing the false alarm. There are three types of false alarm. Okay? Some of you heard about that. Class 1, Class 2, Class 3. Class 1 is quality data, that due to quality data. 2 is due to the looking at the wrong information. And the third one is the decision making. You are not making the right decision based on the data you have. So the three classes of false alarm are doing that. Exactly what they are looking for, the plane in near Australia, they had false alarm. What could be? Maybe they were looking at the wrong place. That's one. Or even that they look in the right place, but maybe the data is contaminated. The sea has a lot of contamination of that. So it's causing false alarm. So false alarm is another problem. It's very common to operation monitoring that get to handle it. This group, I don't think you have been addressing the false alarm problem yet. But again, you have to look at good quality data, You have to look at the right data. You have to make the right decision, human right decision making to make the right outcome.
Thank you. More questions?
To go one step further on that last point, it'll be interesting from an experimentation perspective to look and see if your predictive analysis on failure on oil rigs becomes highly accurate. It'll be interesting to watch the bean counters get involved and start buying cheaper materials, because if they can predict it's going to fail, I'm going to start buying pipe from Walmart, and they can predict it and it can be cheaper in the end.
That was another outcome, so-called you are pushing that diagnostic too far. You started cutting corner. All right. In fact, the Defense Department get into that problem. That you were just one street away from me. Okay, I was at North Fairfax Drive. You guys were next block when I was at O&M. Okay. So what happened is this: exactly what they do. I'm taking a case study of a corrosion problem. The landing gear of aircraft on the carrier for the Navy. So we look out at a diagnostic scheme, what kind of landing gear, what you monitor from time to time, you check what it is, right, the pain and all those. The manufacturer, I'm not going to name the company, in fact, you know whom I'm talking about, they outsmart that. They bring in, the landing gear will not have a problem like that. They bought cheaper material. Exactly what you're talking about, get it from Walmart. Okay, to optimize the reliability problem, okay? But fortunately, the Defense Department, we caught it before they put on the landing gear. So yes, there are people trying to exploit that reliability model. So certain area you could stand a bigger risk, and they were exploiting it, put in cheaper material. Okay, so again, not just reliable, saving costs, is also to make the right decision in design and manufacturing.
Right, thank you, Ken. Please give him a big hand. Since time is running out, I'd like to just extend this session with the Q&A with the audience and all together panelists together. So we'll give a chance to Mike to talk.
A number of years ago, I worked for an oil company, and we had a problem not on the rig, but with the catalytic crackers. Because when you do catalytic cracking, you need to get as close to the theoretical limit of cracking to increase your efficiency. But if you cross over, you lose the entire batch. And so what we did is we actually built an adaptive neural network, but not as a black box, but as a model of the reaction that we thought was taking place, so that we got about an 80% response. And then we took those networks and we adapted them against the performance of each cracking unit to optimize it, and we could get over 99.5% efficiency out of doing that kind of approach.
Right. Again, the neural network is a kind of model of the human behavior, right? You're using the neural network to model the human thinking.
Yeah.
Decision. Well, depends. Some you could be using a physical, some could be using the human mental decision making. So you're using that at the last part of it. On the decision making, what should you do? What do you have? And using that as your decision-making process.
Were you using the neural network as a learning model? And
We-
training in front of big data?
Yeah, as opposed to using it as a black box, we actually used it to develop and test hypotheses. So we evaluated it during the training process and compared it, and we would find that things would get preferentially learned and then lost along the way, so that we learned how to adapt that and do it in stages.
So I think it's really interesting that a lot of these presentations had a lot of feature detection, sort of thematically. I don't know whether you guys organized it that way. I guess one of the questions that I think is really interesting and Gary brought up was how do you do feature detection in an environment where there may be human intentionality? So I'll just give an example for Thomson Reuters. In many of our systems, not only the ones in IT and science, but also the ones in finance, we're very interested to understand whether it's essentially robotic activity or whether it's human. And I think I was talking to Larry earlier, and he brought up the case of people doing some study on sentiment analysis and Twitter feed that we've done within our finance organization. And the observation was, you could actually make money by doing this, doing short-term day trading. I think the interesting question for me about that is, okay, once people are aware of this, once we do the academic studies, we detect that feature, will people be able to script up something so you get the market balance back, right? And it becomes no longer a feature of interest. So in an environment like that, how do we determine, and I'll go back to my case, scientific discovery, how do we determine, using, for instance, our customer access to the Web of Science as a proxy for things people are interested in the scientific community, or using Alex's case of academic search, how do we determine when there's just a robot out there that is sort of pulling down information versus a human versus a hybrid situation where there's a human who has scripted something up and they're looking for something specific, but they're trying to do it at relatively a large scale. So I just think it's an interesting question for us to all think about as we look at how do we analyze this big data.
Thank you, Brian. Anybody would like to comment additional? Larry?
So that invites the question of, can you make a model of intentionality? And that's certainly a speculative question that could get looked at in the future.
Or is being looked at now.
Tony, would you like to comment on sentiment analysis from a social network analysis?
There are a lot of work going on doing semantic analysis sentiment with the social media. So recently, Science published a paper just last month. A lot of traps in the big data science. So they think the finding is basically use the social media analyzing the epidemic disease stuff. Okay. The social media result was kind of twice false alarm generated compared with the CDC real report. So that finding base suggested that all these kind of models, they're not good enough to handle the dynamic situation of the data set collected from social media. So I will send the link to the group. So these are really a very good article about how to use the social media, how to prevent this kind of larger false alarms generated from big data analysis.
So the big issue is how we do meaningful analysis for real business values, not just processing big data.
Yeah.
Michael?
I think a caveat that we find, especially as you're looking at big data and thinking or being seduced to the idea that you now have a lot of potentially more statistical significance, is that there's a tendency sometimes to use statistical tools because of the amount of data that you have. And some of the statistical tools do not allow you to see the unique observations that are the real critical ones. An example is we were looking at three-dimensional structure of proteins, and we went to want to identify features in the patterns of the structures. The statistician said, well, we can apply Fourier transforms and immediately represent all of the three-dimensional folds. We can do that with anything. I said, but the problem is, we know biologically that two proteins may differ by one amino acid. And that will be lost in the Fourier transform of those two proteins, so we can never recover it. And so the message is to make sure that as much of the knowledge of the model and the underlying processes is incorporated in the approach that you decide to use, so that you know what the constraints are and what you are going to be able to find or not find, and being able to reproduce things that you know should be there.
So that's an issue like a correct modeling, accurate modeling. So what technology could help us to model those biological systems more accurately, semantically? So ontology is good enough, or we need some other techniques, Tony?
I think in that article, basically one of the problems the group identified with the Google, a lot of people use the Google search to find the social media information, the epidemic stuff. So the finding they use kind of traditional statistical modeling tend to overfit the data set, okay? So that's why they said for the Google team, they released their kind of algorithm, find that they use 20 kind of variable, try to fit millions of dimension data set. So they kind of, so one of the suggestions that the group, they reported the science paper is basically the way to go is try to use deep learning. So this is kind of the trend. So another recent finding from the Facebook is basically they use deep learning. They can identify the image like a human face image as close as accurate as the human being itself. So this really kind of suggests deep learning is a very promising way, at least for our CVDI centers, because our clients, our members, have a lot of complicated data. Their relationship is more than linear relationship.
All right, I'd like to conclude this panel with one observation and one article that I read here. Until just last November, Google flu trend was considered a wonderful, accurate outcome from analyzing big data. But here, someone analyzed, actually Harvard and MIT analyzed that Google flu trend failure is more than 50%. So it's not accurate anymore.
That's
so this means
the science
good data is very important rather than just a big data. So big data has a lot of spurious, unnecessary, meaningless data. So how we extract right, meaningful business data to create an accurate model, he said, and the accurate data can be talked about it. How we avoid missing data. So I think a big data that just does not mean meaningful. We have to find the right business value by extracting right, meaningful data. Right. Thank you for attending this panel, and then we appreciate all of your discussion. Thank you very much.